Here's week 4 notes for Chemistry 1010. We're going to talk about chemical and physical changes, things from the periodic table that are important: protons, electrons, neutrons, and then electron configuration. Now, what is going to be important to know when it comes to chemical and physical changes is that a change occurs where a new product is formed and it has different properties. So that's a chemical change, meaning if you test the properties of something before a chemical reaction, the properties will be different than the properties after a chemical reaction. And in your lab, you test the conductivity meaning if it conducted electricity before and after. You saw when you dissolved salt, or you took the conductivity of salt, it was negative. Dissolved in water, you evaporated the water, you tested the conductivity of that salt, it was negative. Therefore, that was a physical change. However, you tested the conductivity of magnesium and found it to be positive. You reacted it, magnesium with oxygen, created something called magnesium oxide, and a new substance was formed. The conductivity of that magnesium oxide, that whitish powder, was negative. Therefore, you changed the properties of that compound. You can physically see this going on with your ALEKS modules. You can look at substance X above. If a new substance forms, like in change 2 and change 3, then a chemical change occurred. If no change occurred and the substance is the same, then it's a physical change. However, at least for these here, or probably rationally, ALEKS does something where it keeps the substance the same but makes more of it. So, law of thermodynamics is you cannot create nor destroy matter, meaning the same amount of particles, no matter what changes, the same amount of atoms has to remain the same. That's why this one ends up being impossible. Now we have some examples where something freezes, like change 2. Anything that ever goes from like solid to liquid to gas, or vice versa, or even if it goes from a solid to a gas, which is called sublimation, or gas to solid, which is called deposition, it is a physical change. The change 1 would be impossible because you cannot change the atoms themselves, while change 3 would be a chemical change. Physical, impossible. Now, there's important things that anybody taking college chemistry need to know. One of them about the periodic table is the group families. So all of these are color-coded, and you have to know where the alkali families are. For at least Unit 1 test, you have to know alkaline, the transition metals, the semi-metals, the noble gases, and then these are the lanthanides and actinides, or the rare earth metals, and the halogens. You're going to learn where the metals are and the non-metals are very soon. As I said in class and here, you have to know where the semi-metals are, otherwise known as metalloids. And on the periodic table you were given, it gives a sort of staircase. Everything touching that staircase is a semi-metal other than aluminum, which is a metal, which we'll talk about later. But knowing how to divide the left and the right on this periodic table is important. Thus, asking what are metalloids or semi-metals is fair. Note, hydrogen is not an alkali metal. So all of those families, you have to be able to identify them quickly, and if I ask where they are or an element from them, you have to know almost secondhand nature where to go. Some other things that you have to know from this table are the group numbers 1 through 18 at the top, and the period numbers, which are simply like a sentence cross, and there's 7 of them. Something that is good to introduce to you now before you need to know it at a deeper level is valence electrons. But all that's pretty easy in the sense that group 1A, group 1, group 1, 2, skip 3, 4, 5, 6, 7, and 8, with helium having 2. Valence electrons are outermost electrons. That definition I will not have, but eventually it will. However, as given to you with Alex and in lecture, you have to know how many valence electrons are in each group. Group 16, you have 6, or the halogens, you have 7, or the noble gases, you tend to have 8, but helium only has 2 electrons, so you can't have 8 valence electrons if you only have 2. You also have to know the charges of these groups, the charges, the ion charges that it forms, but I believe later there is another periodic table where it will be a good time to show you that. The link to the periodic table you will always get. So here's a pretty easy question when it comes to valence electrons. Iodine is a halogen, so I know that it's going to have 7 valence electrons. Silicon is in group 15, below carbon, sometimes known as the carbon family, but that is not part of the color-coded periodic table I showed you earlier. So all you have to know is group 14 and 4 valence electrons. Period and group should be pretty easy for you to determine. Right, so I see why I taught this earlier in the lesson, because you do have to know the group charges before I thought in these notes. Group 1 elements, or the alkali metals, including hydrogen, all form a +1 charge, +2. We're going to skip +3. I personally just start at the end. 0 for the noble gases, -1, -2, -3. And zinc is always a 2+, and silver always a +1+. Something that you'll have to do is be able to identify the amount of protons, electrons, based on the atomic number of a periodic table. The only time that you're going to use this bottom number right now is if I ask you to find atomic mass or the molar mass Otherwise, when you are determining protons, electrons, neutrons, do not use that number. That top number is known as the atomic number, which determines the element. Every element has its own atomic number. That atomic number is equal to protons, which is also equal to electrons. As just mentioned, that is true. Then protons plus neutrons equals mass, which is something, again, you have to know. And then this here, we're going to review. No, protons are in the center. Protons and neutrons are in the center of the nucleus. And electrons are on the outside of a nucleus. Nucleus being the center. Protons are positive, neutrons are neutral, electrons are negative. Electrons are flying around, therefore have little to no mass, or at least in comparison, its mass is nothing, or assumed to be nothing. So you'll be tested on whether you know this by essentially using tables. You know protons and electrons are equal to each other. Protons atomic number equal to each other. Protons plus neutrons equal mass number. From there, you can sort of see the pattern of all these working. I guess I'll pick two near the bottom that I don't know if I did in class, but the second last one is MO. It only gives us neutrons, so we have to determine a lot more about MO. But we can look at the periodic table and see it's molybdenum. I'm looking at the symbol and you can tell that. The mass number, I'm going to wait. The atomic number is 42. Protons is 42. 42. Mass total number is 96. Therefore, the molybdenum hyphen notation is at 96. Isotope notation, 96 at the top. Atomic number at the bottom. And so I'm sure you understand how to do those. So this slide provides a good learning experience in that why you don't use the bottom number on the periodic table. Now, when I made these notes, I googled proton, electron, neutron sheet, and it popped up, and some teacher made it. I think they just wanted to mess with whoever didn't want to make it themselves, because the ones on the back are technically impossible. Hydrogen is possible here. Symbol, mass number, atomic number, protons, neutrons, electrons, 1,1H. But for the ones below it, we're given electrons. You can't determine mass number without neutrons or mass number, meaning you have to be given either neutrons or mass number to solve it, because the bottom number is an average of lots of different atoms, and these are specifying 1. And so really none of these are possible to do. And you can't use the bottom number. So if you did use the bottom number for like magnesium, the bottom number is 24.31. You can't have here, you can't have 12.31 neutrons. It's one individual item. So these are impossible to do. The last one is possible to do because we do get neutrons. But I think it was just someone messing with us. And I respect them for that. So quickly, I'm just going to remind you of the charges. Plus 1, plus 2, plus 3, 0, minus 1, minus 2, minus 3, zinc, silver. Electrons are out here. They form ions by either leaving or entering the cell, or the atom. Let me give you an example of 2, where I'm giving you the full notation. So let's say I say the ion for magnesium. How many protons, electrons, neutrons are there? Magnesium is in group 2, the alkaline metals. So you know that forms a plus 2. I would have to give you the neutrons. So I guess I could give it to you in isotope notation. So if I said 25 and 12, protons here would be 12, electrons will be 10, because you are losing something negative. So electrons can change. Electrons are negative. Therefore, to become positive, you have to lose something negative. Neutrons here be 13, and I guess mass would be easy because that would just be this. Compared to, let's say if I said for sulfur, what is the ion for sulfur? You're going to look at group 16, protons. You see sulfur is element 16 as well. Electrons, it is a negative charge. So it has to gain electrons to become negative. Neutrons, we can only determine with mass. So let's just say the mass is, I don't know, 80. It wouldn't be that, but it doesn't matter. Who cares? And therefore, the amount of neutrons will be 64, because protons plus neutrons equals 80. But the important thing here is seeing that electrons change in comparison to protons. And you know how much they change based on the charge, and you know what they initially were based on the amount of protons. Do an example. I think I'll do some on the next page because I probably did these in class. So here, looking at that last one, there's 29 protons. So I know that is copper. The atomic number is 29, as protons equals atomic number. Notice how it has 2 less electrons. Let's see, U2 plus. And the neutrons is going to be 35. The example above it shows copper as well, but this time it's a plus 1, so only lost 1 electron. The mass number, because it's neutrons plus protons, remains the same for this problem. So then we can look at the next one. If you want to just look at protons and electrons, we know that it's going to be a 2 plus. Protons number 26, this is iron. Atomic number 26, neutrons 30. Symbol iron is Fe. It forms a positive charge, is a cation, so cats have paws, and then positive, like a paw. And onions or anions are negative. Remember Reminder that hydrogen is not a alkali metal. So now we're going to do electron configurations. What I do want you to know is electrons are negative, which you do know, and the center of an element, of an atom, is positive. And if we look back at the picture, you have those positive and neutral charges in the middle and electrons on the outside. Electrons and protons are attracted to each other, but they repel each other, meaning electrons repel just like two negative sign magnets will repel. Then the negative are attracted to the positive in the center. So when we do electron configurations, we're essentially writing the dance moves of the electrons dancing around the protons, because they want to be as close to the center as possible, but as far away from each other as possible. Being that as such, no two electrons can be in the same place at the same time, so every electron must have its own quantum number. To get two electron configurations, you have to first be able to write them. And one way that I do that is I have a 1s, 2p, 3d. I can make this a little bit longer. 4d. And I'm just going to circle some elements and I'm going to say what it ends with. So if I circled this element, that ends in a 4p4. Why? Because this goes 2 across, or I'm sorry, that goes 2 across. That's 0, 2. This goes 10. And this goes 6. So, alright, circled, that's 4p1, 2, 3, 4. That is 4p4. If I were to circle, let's say this element right there, that's going to end in a 5d1, 2, 3, 4, 5. 5d5. If I circled this element here, that's going to end in a 4s1. So I'll do some examples. I'm just going to circle the element and we'll do the examples and then I'll skip the Alex ones. But let's say circle this element right there. If I go 1s, 2p, 3d, I can say that that's going to end in a 3p3, but we have to get there. So you always start off with the 1s2, 2s2, 2p6, 3s2, 3p3. I can count up the superscript on the electron configuration and make sure it matches the element that I circled. So superscript for 1s2 is 2, 2s2, 2, so plus 6, 10, 12, 15. Is element 15 right there, 3 over. And phosphorus is element 15, and it ends in at 3p3. If I drew now, if I ask for the electron configuration, so I'll change the color here for that one. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. you can add up the top numbers and it would add up to vanadium or 23. Now, maybe somewhat of a curveball, but not really too much, is if I ask the electron configuration for hydrogen. Well, that's just going to be 1s1. Or for helium, it'll be 1s2. Lithium will be 1s2, 2s1. Beryllium, 1s2, 2s2. Now, sometimes electron configurations are rewritten in order of principal quantum number or the front number. And I'm bringing this up because every time I teach this, students will go, well, 1, 2, 2, 3, 3, 4, 3. So that D, you're not doing it wrong, but it does go down in number there. And that's because each one of these moves differently. S orbitals move in circles, P move in figure eights, and D sort of like a clover. And that front number is how far away it is from the center, and is based on the geometry of the movements and the goals of the electrons repelling but being attracted to the center. That's why D goes down a number. So I'm going to introduce to you here the shorthand notation and quantum numbers. So this element right here, that's going to end in a 5s2. And I do not want to write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. I would rather just be able to abbreviate that. And if you know how to do electron configurations, doing so is not too difficult. In that, we can go to the noble gas before it. Kr. I'm putting brackets around and finishing it off. 5s2. Now, that's not what the directions say here. Write the electron configuration. It does say write the full electron configuration, but that is how you do the abbreviated notation. I think I'm going to do examples at the end for quantum numbers. So go to the end of the video if all you care about is the quantum numbers. The abbreviated notation, again, I'll do quantum numbers later, is going to be helium, 2s2, 2p1. That ends in a 2p1. I go to the noble gas before it, and there it is. The abbreviated notation for this one will be argon, 1, 2, 3, 4s2, 3d1, 2, 3, 3d3. So ignore this little gap here on table for Alex. Again, I'll do quantum numbers later. There are some exceptions to electron configurations, but those are, you don't have to know those. This stuff is all pretty easy, which you can practice in Alex, and again, I'll do quantum numbers at the end. Here we are looking at the electron configuration and determining. This is the shorthand notation, we're going backwards. So if you start at helium, you can work your way up to P2, which is Si. And again, like I said before, that you can look at the last one and determine the full electron configuration, or what element it is. So again, I'll do quantum numbers at the end, but I want to show you how else I can test this. What is the magnesium, or what is the electron configuration of the ion magnesium forms? Let's say if I just were to write the electron configuration of magnesium: 1s2, 2s2, 2p6, 3s2. Magnesium forms +2 charge because it is an alkaline metal, which means it loses 2 electrons, and therefore 1s2, 2s2, 2p6 loses 2 electrons. So the electron configuration of an ion that magnesium forms would be 1s2, 2s2, 2p6, or the same one as neon. So you're going to learn very soon that noble gases are very stable. The elements will lose or gain electrons to have essentially the same electron configuration as noble gases, or to have the same amount of valence electrons as noble gases, which, as you know, noble gases have 2 or 8 valence electrons. Helium has 2. So helium is a noble gas, has 2 valence electrons, the rest have 8. What is an electron configuration for a halogen? So you know halogens are group 17. I'll write chlorine's electron configuration. Chlorine is element 17, which means it has 17 protons, 17 electrons. If you look on the periodic table, I can count down from 2p to 3p, 3p5. It should end with 1s2, 2s2, 2p6, 3s2, 3p5. I can count the superscript. I'll add up to 17, which does match chlorine. However, I said ion. Halogens form a -1 charge, making it an anion. Means it gains an electron. 1s2, 2s2, 2p6, 3s2, 3p6. It has one more electron, and again it follows that same pattern as being a noble gas, and essentially it went from having 7 valence electrons to 8. So here I'm going to explain how to find the 4 quantum numbers of an electron, of a specific electron. So we know we have S, P, and D. S for the second quantum number is always going to be 0, P1, D2. Every orbital can fit 2 electrons, and since S is 2 across on the periodic table, we have 1 orbital, or 1 box. P is 6 across, so it starts with boron, carbon, nitrogen, oxygen, fluorine, neon. Each one can fit 2 electrons, so there's 6 total electrons in there, so 3 boxes. D has 10 electrons across, 2 electrons per orbital, so 5. Underneath that, I'm going to write a number. I'm going to start in the center, 0, 0, 0. To the left, I'm going to write negative numbers. S doesn't have any more boxes, so it ends with 0. P, negative 1, positive 1. D, negative 1, negative 2, positive 1, positive 2. So if I ask for the 4 quantum numbers of the outermost electron of an element, you have to use one of these 3, depending on which area it is in. Now, I'm going to fill up these boxes how they should be filled in a specific order, as electrons want to be as far from each other as possible, but as close to the protons as possible. If I write protons over here, that's just for learning purposes. The S electron is going to go up, down, because they spin in opposite directions. P, let's say I want to fill up 6 electrons in P. I'm going to go protons are right there. Electrons are going to go up. The next electron wants to be further away from the first electron. Up, up. The fourth electron has no choice, so it would rather be close to the other electron while being as close to the proton as possible. Down, that's 4, 5, 6. So they go in that order, and there's a rationalization of that. So up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how I just filled them is the order that you should fill them. So I think we should just practice them and get in the habit of looking at maybe the pattern associated with it. So let's say I go, what are the 4 quantum numbers of the last electron in chlorine? Go to the periodic table, look at chlorine, and I want you to think to yourself, well, what does chlorine end with? We know that boron there ends with 2p. Below that, aluminum ends with 3p. Count over to chlorine to 3p5. The first quantum number, otherwise known as the principal quantum number, but the names of them I'm not worried about, is 3. The second quantum number follows the pattern of S being 0, P being 1, D being 2. That electron is a P because it says P, and it moves like a figure 8. We need 2 more numbers to distinguish that electron from any other electron. So we have a p orbital, which has 3 boxes, or 3 different orbitals is probably the better way of saying it. And we have 5 electrons in those 3 different orbitals. Up, 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 3, 4, 5. I drew those, center being 0, left being -1, right being +1. The last electron I drew is that electron. And since it's in that box, it's 0. Since it's pointing down, it's -1/2. Now that is telling us which way it's spinning, so the principal quantum number is how far away it is, the orbital number. The second is the shape of how the electron's moving, the momentum, and the spin. So all these electrons, again, are frantically moving in ways to avoid each other, but to snuggle up with the protons in the middle. So let's try another one. If I were to pick zinc, element 30, what I want you to do is look at that periodic table. Look at where zinc is, element 30. It is a transition metal. And what you really need to be able to do right now is know that it ends in 3d10. That first period in the transition metals starts with a 3. Zinc is at the end of that. It is a 3d10. First quantum number, 3. Front number. S equals 0. P equals 1. D equals 2. It's a D, so that's 2. How many boxes or how many total orbitals are in there? Well, there's 5 because you can fit up to 2 per orbital. There's 10 electrons, so let's fill it out correctly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's a full orbital, but I'm having you identify the outermost electron, which would be right there. You're going to learn later why those electrons are essentially want to be identified. Middle number is 0 minus 1 minus 2 plus 1 plus 2. That last electron is a plus 2. That last electron is pointing down, negative 1/2. 4 quantum numbers for that zinc outermost electron. 3, 2, plus 2, negative 1/2. Now I'm going to pick the 4 quantum numbers for a alkali metal. So let's say if I ask you what are 4 quantum numbers of an alkali metal? Really, 3 of the 4 are going to be the same. I'll just pick one. I don't know if that makes sense, but I'll pick one here and we'll do that in a bit. So let's pick rubidium, 5s1, ends in a 5s1. 1 box. Principal quantum number is 5. The next number is 0. It's pointing up. Well, I mean 0 there. Positive 1/2. So really every alkali metal is going to have the same 3 of the 4 same quantum numbers. The element above that would be 4. So the element in the period above that would be 4. So potassium above that, sodium 3, above that lithium 2, and then hydrogen would have 4 quantum numbers of 1, 0, 0, positive 1/2. So now I'll just pick any random element and write the quantum numbers for it. So we did zinc. I'm going to do tungsten. So element 74. That's going to end in a 3, 4, 5. D4. 5, D2, next two numbers, up, 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 middle number 0, minus 1, minus 2, plus 1, plus 2. The last electron right there is a plus 1, and it's going up, so it's plus 1/2. So 4 quantum numbers of tungsten. Maybe another way of even showing this here is let's pick the quantum numbers of each one. We have 0, minus 1, minus 2, plus 1, plus 2. This is going to be a -2 plus 1/2. This next one, if that was the next electron, it's going to be a -1 plus 1/2. Next electron, 0 plus 1/2. Next electron, plus 1 plus 1/2. Next electron, plus 2 plus 1/2. Pointing up, positive 1/2. Pointing down, negative 1/2. So that next electron, if we had a D6, so if I got rid of all this here, D6, that'd be pointing down. The next one, those quantum numbers are going to be -2, -1/2, because it's going down. Next one, -1, -1/2. Next one, 0, -1/2. Next one, 0, or no, sorry, +1, -1/2. Down, +2, -1/2. So, yeah, I don't know. I think that is enough practice.